Hi, I'm Ozan Unal, and I'll be presenting our work, Scribble-Supervised LiDAR Semantic Segmentation. As motivation, let's begin with the task of LiDAR Semantic Segmentation itself, where the goal is to classify each point with a label. To employ fully supervised training, we need a lot of annotated frames. A single frame can reach beyond 100,000 points. It's easy to see how annotating a large-scale dataset can become very expensive very quickly. Our goal in this work is to alleviate this tedious labeling process. In the first part, we will introduce a weak annotation strategy that can reduce labeling times by tenfold. Of course, naively working with such weak labels will undoubtedly result in a loss of performance, which will set us up perfectly for the second part, how to deal with such weak labels. So let's begin by introducing Scribble-Kitty, the first Scribble-annotated LiDAR Semantic Segmentation dataset. We base Scribble-Kitty on the popular Semantic-Kitty dataset. However, unlike Semantic-Kitty, our dataset only contains 8% labeled points. When annotating, we use lines as scribbles. As LiDAR inherently preserves the metric space, this labeling strategy allows fast and effective labeling of structures that span large distances. Compared to dense annotations, we reduce labeling times by tenfold. As mentioned before, naively training with such Scribble-annotated data results in a considerable performance drop compared to the fully supervised setting. This is caused by the lack of available supervision. Remember, 92% of the data remains unlabeled, which means 92% of the data is not being used to supervise the model. We address this issue by introducing three standalone contributions that can be paired with any off-the-shelf 3D semantic segmentation model. Now, let's take a look at each module one by one. Firstly, to utilize the unlabeled points in our data, we extend the supervision in a weak manner by using a mean teacher framework. We introduce a consistency loss between the student and the teacher that is applied to only unlabeled points. While the partial consistency loss does extend the supervision to unlabeled points, the teacher continues to inject uncertainty to the student. In order to more directly utilize the confident predictions of unlabeled points, we introduce our second contribution, a novel class range balanced self-training scheme where we strategically fix the teacher's predictions. Now, the task of generating good pseudo-labels is not trivial. The class distribution in autonomous driving scenes are inherently long-tailed, thus head classes often dominate pseudo-labels. Furthermore, LiDAR point clouds become sparser by range. Distant points therefore show an overall confidence drop and thus lack representation in the pseudo-label set. To reduce possible biases introduced through self-training, we employ a novel class-range balanced pseudo-labeling strategy and expand our dataset accordingly. To distill the newly introduced information and therefore more directly utilize the fixed initial teacher's predictions, we retrain our mean teacher framework. Finally, let's talk about our last module, augmentation. Going back to the observations that motivated our annotation strategy, we note that since LiDAR inherently preserves the metric space, semantic class relations that are governed by our societal norms are also well preserved. For example, cars lie on roads, vegetation appears on terrain, and often structures border ground classes. To exploit these relations and improve the pseudo-label quality in return, we introduce the Pyramid Local Semantic Context Descriptor. PLS is a novel pyramid-shaped context feature based on a point's local semantic distribution which, using sparse scribble annotations, explicitly provides the network with the information to derive local semantic relations. When we combine all three components, we can achieve 95.3% relative performance when compared to fully supervised training. We further provide ablation studies to show that our pipeline is model independent and can achieve similar performance gains with three different state-of-the-art segmenters. Furthermore, we show that scribbles are a more effective labeling strategy than fully annotating a subset of frames under a fixed budget. To sum up, in this work, we introduced Scribble-Kitty, the first dataset for Scribble-Supervised LiDAR Semantic Segmentation. We further propose a novel pipeline consisting of three standalone components that, when combined with any 3D semantic segmentation model, can substantially close the gap to fully supervised training. Thank you for listening. Using the QR code, you can access our GitHub page where you can download our dataset and view our codebase. Also, make sure you check out our paper.